Good afternoon, everyone. Welcome to day 4. Can't believe it. How are we doing? Surviving? Yes, good. Well, you made it to day 4, and I'm super excited that you've decided to join me for the next 45 minutes or so attending this session. This is DAT314. My name is Shayan Sanyal. I'm a principal database specialist at AWS. Today, we are going to dive deep into how to build serverless chatbots using ElastiCache and Aurora Postgres. Who's using Aurora in production today? Just a show of hands. Oh, majority of you, okay. And who's building chatbots using Aurora Postgres as the database? No one, okay. Well, you are in the right room, so let's dive in. So our case study today is Flightly. It's a fictitious travel platform that allows customers to search flights, book hotels, and plan vacations. Today, we'll crack open the architecture. We'll help Flightly build it. And we'll sort of also see how to evolve this basic chatbot that Flightly has into an agentic AI system. Along the way, we are extracting some reusable architecture patterns that hopefully you can apply in your own systems. Let's dive in. Friday afternoon, I'm planning a vacation to Hawaii. I type my query into Flightly, and it starts thinking. Still thinking, still thinking, still going. So I do what we all do. I go and check my email, and very quickly, I'll notice that this Island Air competitor has a flash sale. Hawaii flights, ironically, great price. Back to Flightly, still thinking. I book with Island Air, done. Flightly just lost me as a customer, and probably thousands of others. Not because the product was bad, but the chat was just too slow. Let me show you what this costs the business. 30 seconds average response time for a single booking. About half their users hit this performance wall. Average booking value is about $300. They handle 1 million requests daily. Now, industry data shows that every second of delay costs you 7% in conversions. With super long response times, even a tiny fraction of users abandoning adds up very quickly. So if you just do the math, it's about $150K lost every day, which compounds to $50 million annually. So how do we fix this? Here's the thing. When Flightly started, they didn't see this coming. They hoped they were building for speed and scale like everyone does, but their team did what most of us would do. They built an MVP, they started quick, launched the platform, user adoption accelerated. But success created new problems. Thousands of users became millions. And suddenly they are hitting this entirely new set of bottlenecks that obviously doesn't appear unless you're at this scale. So the question kind of shifted. How do you maintain sub-second response times when you're processing millions of requests per day? Here's what Flightly's working with. Customer data and company data. It's similar data to what we all have in our databases. Customer data includes things such as past bookings, search history, preferences, etc. Company data is flight inventory, hotel inventory, promotions, etc. All of this data lives in Aurora Postgres. Years and years of rich data. Perfect foundation for a chatbot. But here's the problem. Without a cache, every query hits the database. Every semantic search recomputes vector distances. At 1 million requests per day, you get exactly what we saw. Painful response times. Now, your instinct might be, let's migrate to a faster database. But that includes new infrastructure, new ETL pipelines, migration risk. And Aurora's been rock solid for years. The database isn't the problem, it's the access pattern. So we keep Aurora as our source of truth and add a caching layer. Let's keep that in mind. Let's understand the current architecture. User query comes in, find me a beach resort in Bali. The system queries Aurora as a knowledge base. It pulls relevant context, things such as availability, seasonal pricing, and the user's preferences. All of this gets assembled into a context-aware system prompt. which is nothing but the instruction set for the LLM. The system prompt does two things. It defines behavior, so answer travel questions, reference the knowledge base, maintain conversation history, and it sets personality. Be warm, enthusiastic, helpful. This enriched prompt plus the user's question gets sent to a large language model, which then generates a tailored response. Now, for a single turn conversation, single interaction, single user asking this question, this architecture works great. This is perfect. But watch what happens when we scale this to thousands of users concurrently asking same questions or different questions. So now we have multiple users hitting the system. And in travel, I like to think of it as the Pareto rule. It's 80% of your queries are just different questions, are just 20 questions wearing different outfits. Now watch the latency stack up. The orange lines are your warning zones. The red lines are now we are hitting the limits of the system. Every single query triggers the exact same expensive pipeline. Your query hits your database, there is a distance calculation, fetches context, assembles the system prompt, and sends it to the LLM. Each operation adds about 100 milliseconds, and that stacks up. You'll notice very quickly, you're spending over a half second, over 500 milliseconds per request. And this keeps getting worse. Response times start degrading from 500 milliseconds to 5 seconds to 30 seconds. At 1 million users daily, this architecture is unsustainable. Ask your application teams what's wrong, and I'm sure they'll all point straight to the database. But it's not the database's fault, it's the access pattern. All right, we touched on caching a little bit earlier. Let's dig into why it's essential for conversational AI at scale. When a user asks about baggage policies, frequently asked questions, a cache can serve that in under a millisecond. If it was the database, that's disk I/O, buffer lookups, query parsing, query execution, et cetera, et cetera, et cetera. And that's about 50 milliseconds, even with solid-state drives, SSDs. And every database connection means a TCP handshake, a TLS negotiation, cross-AZ round trip. That's about 5 milliseconds per each iteration. And that's just the protocol overhead before your query even hits the database. API economics. Show me flights to Hawaii probably gets asked thousands of times every day. Each uncached request burns inference costs. There's embedding generation, there's LLM invocations. You cache once, and you amortize the cost across the fleet. Finally, by definition, semantic search and semantic lookups mean cosine distance calculations across these 1024, 1536, 3072 vector dimensions. And you probably have millions and millions of those vectors. So caching those top K results skips those heavy floating point cosine distance operations entirely for those repeat queries. That's the kind of thing that we are looking for. This is the speed layer that we are going to add to our architecture. Now, this is a great segue on why caching is essential. Let's take a little detour to the service side of things. Amazon ElastiCache is our fully managed caching service. It's Redis OSS compatible, Memcached compatible, and Valkey compatible. Your application connects to a single DNS endpoint using standard Redis or Valkey protocol. Behind it is a managed proxy fleet that handles connection multiplexing across this distributed cluster. And it gives you nice features such as consistent hashing, async replication across AZs, sub-millisecond failover, and so on. Of course, you throw in the serverless benefits. Scaling is automatic. Now, this is the speed layer that eliminates Flightly's bottleneck. Let's see how it transforms the architecture. So ElastiCache's shared cluster architecture serves data directly from memory, regardless of which AZ the data lives in. So it guarantees consistent microsecond P99 latencies, whether you are at 100 requests per second or 100,000 requests per second. Now, just before reInvent, I think about a week before reInvent or so, we launched vector search for ElastiCache, and with it, durable semantic caching. With ElastiCache Valkey durable semantic caching, we are actually hitting 90% plus cache hit rates for repeat queries. What that means is 9 out of your 10 requests get served from memory. Third is resilience. Every shard maintains read replicas across availability zones. When hardware fails, and during December holiday traffic, there are high chances that hardware might fail, ElastiCache automatically detects and promotes a read replica to become the new writer. And of course, holiday traffic is inherently unpredictable. Spring breaks might spike 15 times over a normal February baseline. So ElastiCache can monitor that and provision additional shards as needed to accommodate that growth. Now we've solved speed. We are getting sub-millisecond responses. There's another component to this. Now we need intelligence. Your users aren't asking, select star from destinations where activities like beach. They're asking, where can I surf and party? And they don't repeat exact queries. It's the intention. They express intent about those queries. So all of this relates to something called semantic search. So let's see how semantic search actually works. You start with your domain knowledge. This would be travel guides, hotel descriptions, visa policies, etc. For Flightly, it's all in Aurora Postgres. You break this corpus into bite-sized chunks, and then you feed this data through an embedding model. Your text in those documents becomes multi-dimensional vectors, and each dimension captures semantic features. So similar concepts like beach and coast clustered together. Dissimilar concepts will stay apart. In practice, Miami's embeddings will look something like this: pristine beaches plus world-class clubs across, let's say, those 1024 dimensions. And Bali's encoding represents tropical surf beaches plus wellness spas. Both contain beach components, mind you. But then Miami leans towards this urban and nightlife theme, whereas Bali leans more towards spiritual and wellness themes. These embeddings get stored in a vector database. Aurora Postgres has PG Vector. Just a show of hands, who's heard of PG Vector? Okay, quite a lot of you, good. So PG Vector, for those uninitiated, is an extension in Postgres for storing and querying vector embeddings. And this enables that semantic lookup, semantic search. On the other side, now when your user comes and asks this question, where can I surf and party, that query hits the same embedding model and gets converted into a 1024 dimensional vector, for example. Now we run semantic search against Aurora with PG Vector. This is what the query looks like. You never see it. The model handles it behind the scenes. What you do see are top matches, Miami and Bali, ranked by a similarity score. Now this is the intelligence layer. So we had speed, now we added the intelligence layer. This is how Flightly also moves beyond a simple keyword match to understanding true user intent. Now, while this slide focuses purely on semantic search using vector embeddings, traditional keyword-based full text search cannot be overlooked. So Postgres does have a fully featured sort of full text search component as well. And in practice, many of these search systems combine both, a technique which we call hybrid search. Now here, we are centered on semantic search, but if you are interested, there is also a session tomorrow on hybrid search, DAT314. Now a quick detour to the service side. Now AWS offers several managed databases with native vector search, and we keep adding more and more databases to this sort of whole environment and ecosystem. RDS for Postgres supports vector search, so does Aurora Postgres, DocumentDB, OpenSearch, etc. Well, Flightly chose Aurora Postgres since their data already lived there. It was an easy choice. Now in the Aurora serverless architecture, flight search is usually very spiky. It depends on seasonality. Flash sales, etc. The way the architecture works is, again, you have this decoupled compute and storage layer. And with Aurora capacity units, you can control the level of provisioning required for scaling up or scaling down. Now, Aurora IO Optimized, which is a storage configuration, handles this IO-intensive vector search plus your regular transactional search, which is bookings, payments, etc. And there is no performance degradation because of a little bit of better techniques that we do with the IO-optimized configuration. Plus, it gives you the added benefit of predictable costs. Data locality is a big win. So vector embeddings live in the same Postgres tables as your transactional data. This is your booking and customer profiles. No external database needed, no ETL pipelines to set up, no migration risks, and so on. Finally, there is the global reach perspective. So Aurora Global Database replicates across region with sub-second replication lag. A user in Tokyo gets served from the Asia-Pacific replica. A user in London gets the EU replica. Global data, local read performance. All right. Now we have sort of the complete architecture, right? So ElastiCache provides this sub-millisecond performance for cached data. Aurora is our durable sort of semantic intelligence layer through PG Vector. Let's see how these two integrate together. We'll start with the foundational architecture and add in layer-in sophistication as we go. Step one is simple Q&A. This is the baseline pattern. I ask, can you book flights from Vegas to Hawaii? The query routes directly to Bedrock. There's no pre-processing, there's no context assembly, just raw user input. The LLM comes back with a response using only its pre-trained knowledge. And this is typically very generic. There is no personalization here, nothing particular to me as a user. Now, here's the architectural challenge. By definition, LLMs are stateless. They don't remember anything. So they don't maintain any kind of a session state or continuity between interactions. The moment I close this chat, conversation history is gone. So we need a way for the chatbot to remember. So let's add conversational memory using ElastiCache. Step two is adding that conversation history or chat history. Now, ElastiCache is our layer to store that conversation history. So when this query arrives, which is a follow-up, I'm not asking my previous question. It's what about hotels there? It's assumed that ElastiCache has now the previous context, and it can supply that context to my prompt, which will again give me a tailored response. This is the shift. So we have now transformed from stateless API calls into stateful conversations. And ElastiCache provides this persistent session memory. But notice, the responses here are still fairly generic. There's no personalization here just yet. So step three is adding that personalization layer. Now we are evolving a little bit beyond the basic conversation history. I ask another follow-up, recommend activities for my family. Now, ElastiCache's role in this case expands. We are now caching user profile data. This will be hashes containing family composition. So I have 2 kids, ages 4 and 8, activity preferences like outdoor adventures, budget constraints like a $300 max. Now, when this query arrives, using ElastiCache's getAll, you can retrieve the complete preference hash and inject it into the prompt. The LLM will now generate a very tailored response based on my personalized information. Activities appropriate for ages 4 to 8, aligned with outdoor adventures. At this stage, we are not just remembering, we are enriching context with persistent user attributes. It knows information about me, my family, and so on. So ElastiCache in this use case provides both ephemeral session memory and it provides the durable preference storage. This is the shift from remembering to understanding. Now we are onto the final stage. So this is contextual intelligence, also called retrieval augmented generation. I ask cheapest flight options for next month. That's it. Aurora Postgres enters the picture. The application generates an embedding, executes a semantic search against the flight model, routes matching cheapest options filtered by whatever date range that I provide, joined with real-time pricing to give me a very tailored response. This is RAG in action. We are now using ElastiCache for that sub-millisecond session state and preference lookup, but we are also using Aurora for grounding the data in our domain knowledge through semantic search. Together, they are providing this fast, personalized, and accurate customer experience. So far, in 4 steps, we've built a pretty sophisticated conversational system. It has memory, it has chat history, it has personalization, and it has contextual intelligence. But remember, we are still at the stage of a chatbot. What if we could go beyond simple Q&A? What if it could go beyond just giving us information about hotels availability, flight availability, go one step further and start booking those for us? That's the shift to agentic AI, from answering questions to taking actions. Before we get into the agentic layer and the architecture, let's see how we got there. It's important to keep this perspective in mind. Before we knew it, 2 years ago, we started with GenAI chatbots. Singleton, rule-based, constant human oversight. Then came in GenAI agents, goal-driven systems that plan, reason, and use tools. A booking agent will go and search flights, compare prices, execute workflows, but still single domain. Now we are stepping into the era of agentic AI. Multi-agent systems where specialized agents coordinate very nicely. Your booking, your customer service agent, your recommendation agent, all communicating, delegating with minimal oversight. This is what we are building for Flightly. Let's look at the architecture. So same travel question as before. The agent retrieves cached context, in this case from Valky, all in parallel, remember. So HGetAll for user profile, LRange for conversation history, gets for session state. Sub-millisecond retrievals, super quickly you assemble your complete user context. Simultaneously, we are doing a semantic search against Aurora. Query vectorization, similarity search, this will be typically in 2-digit milliseconds. User personalization from Valky, domain knowledge from Aurora. Now is where it gets interesting. Tool invocation through another concept called Model Context Protocol. So MCP provides a standardized interface for LLMs to communicate with various services, things such as APIs, databases, what have you. The agent can also call external APIs, things such as weather forecasts, travel advisories, FAA regulations, etc. So the result of all of this becomes a super personalized, actionable response. The agent asks if you would like to book or explore other options. This is promising, but how do we actually implement this? This is where Strands Agents comes in. It's an open source SDK for building AI agents. Lightweight, model agnostic, supports Bedrock natively, but it also goes beyond and has integrations with OpenAI, Anthropic, Ollama, etc. It handles this multi-agent orchestration, provides native MCP tool support with over 85 tools available, and you can also integrate your existing APIs with custom tools. We'll look at a few examples later. Let's look at the code. So building an agent with Strands is relatively straightforward. You have certain primitives, and you just have to implement those. First, you import the core primitives and configure your LLM. In this case, we are using Claude Sonnet 4 on Bedrock. Second, you create the agent. It's as simple as that, one line of code. That's it. So now you have a functional AI agent, but it's super limited, right? It can only do simple Q&A. It doesn't have any capabilities just yet. So let's add capabilities. Now we start defining the system prompt. Remember, this is the personality of the agent. Flightly's personality, domain expertise, behavioral constraints all go into the system prompt. Your Flightly, a travel assistant specializing in flight booking and travel itineraries, provide clear, concise, and professional responses with helpful options and pricing. So if a query comes in, something like flights from Vegas to Hawaii, the agent responds in character. It'll have a travel domain focus, it'll use a professional tone, give you actionable options with the pricing. But remember, agents can also take actions. This is still simple Q&A. So let's add some tools, which is the ability to act. So the fastest way to give your agent access to the Aurora Postgres database is via the Aurora Postgres MCP server, which becomes a tool for the agent. With the Aurora Postgres MCP server, you connect directly via standard connection parameters, the ones that you're already used to. So your host name, your database credentials, there is no custom tool implementation. You are not writing any handwritten SQL wrappers. The benefit is there is no maintenance overhead. Anytime your schema evolves, you can just use your standard credentials to connect. Now, Strands provides a list tool sync API, which you'll see on line number 16, which discovers these tools automatically. These could be your MCP servers plus your custom tools, APIs, databases, etc. Now here, Aurora Postgres as an MCP server exposes a couple of tools, get table schema and run query. Get table schema is for schema discovery, and run query is for running SQL queries. So in this case, when we import our tool and then make the tool invocation, the call to database is about 2-digit milliseconds, which is typically what you'll have with a direct connection as well. But then notice this line. There is a persistent MCP connection. There is zero overhead of reconnection. Anytime in Postgres you're trying to reestablish a connection, there is a lot of overhead. There is TCP handshake, TLS negotiation, auth, etc., etc. So MCP eliminates this whole bottleneck and uses a persistent connection to the database. The other benefit is, of course, you get to directly you don't have to write your own SQL query. If you don't know SQL, your agent handles that for you. All right. But your MCP servers can actually go beyond these databases too. Remember we talked about weather APIs? So in this example, let's add a weather API. Same pattern, now for weather. There is a special sort of symbol that we use, the MCP tool decorator, which you'll see. This defines a function calling OpenWeather API externally. And this code snippet actually exposes the weather data API as an MCP tool to the agent. Our Strands agent connects in the same way, just like it did to Aurora, but same protocol, different capability. But here's the production challenge. 1 million queries daily, many semantically similar, weather in Hawaii, weather forecast, Hawaii forecast, temperature in Honolulu, etc., asked by a number of different users. Each triggers an API call. Expensive, slow, and unnecessary. So we need some sort of intelligence that goes beyond these standard MCP servers. We need intelligence with tool caching at the tool layer. So standard MCPs don't cut it. So let's go a little bit beyond and add in custom tools. Now, I've mentioned tool a lot. Tools are nothing but simply Python programs, functions that give business logic or execution logic to your agent. Simply Python functions. The tool decorator here gives you full control over execution logic. Here's an example. So search flights takes origin, destination, optional date, but then the doc string, which is the argument, provides schema information the agent uses to understand when and how to invoke it. Here's where it gets powerful. Tool logic defines that check val key first. If the thing exists in my cache, return the results in under a millisecond. If it doesn't, query Aurora. There is a first-time penalty. It'll hit the database, yes, but cache the subsequent results to the val key layer. Again, predictability sort of maintaining there. The key takeaway you'll notice here is you want to use MCP for things like schema discovery and non-critical paths. But you want to use custom tools when you need capabilities beyond what MCP provides, or when performance is critical. This is the user output. Anytime your query doesn't hit the cache, it's going to hit the database. Again, 2-digit milliseconds, about 85-ish. But then the second time is the benefit. We start getting those benefits right away with the val key caching layer. All right. So we've built Flightly's complete architecture. Now let's extract some reusable patterns that we'll use, which are basically blueprints you can apply right away to your own applications. Pattern 1 is context cache. John asks, what about hotels there? The agent goes and queries val key, retrieves John's complete context, remember the whole parallel operation, chat history from the Hawaii flight discussion, session state, user preferences, etc., etc. Simultaneously, it runs a semantic search with Aurora database. In the end, all of this generates a contextual, context-aware response, taking in John's preferences, etc., etc. And this pattern is universally applicable. You can apply this to customer service agents. Imagine maintaining ticket context, virtual assistants, which will need to remember preferences across sessions, healthcare chatbots tracking patient history, any system where you think conversation continuity matters, you need that quick context retrieval, this pattern will apply. All right. Pattern number 2 is embedding cache. This is where we accelerate the semantic search by caching vector embeddings. Pretty neat. Think about users searching for things to do in a new place. These are almost always short keyword-based lookups. And chances are a lot of those users are asking same repeat questions all the time. If I go to Japan, iconic temples in Kyoto, best food in Tokyo, etc., etc. The first encounter, of course, is going to be to the database. And there's this whole embedding pipeline that you have to go through, typically completes in about less than 200 milliseconds. But then the subsequent retrieval is through the caching layer, which is where we get the advantage. And given that these are serverless services, both of them can scale in place, up or down, in or out. Now, pattern 3 is interesting. This is the durable semantic caching by ElastiCache. So your data sources come as natural to your embedding model like before. This is the whole pipeline. But a lot of the times, remember I said people phrase things differently. They won't be asking the same questions. What are the best beach destinations in Hawaii? Can you recommend beach resorts in Hawaii? Yada, 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 and so on and so forth. Now, without semantic caching, this goes through this entire pipeline to get to the response. Now, there is, of course, LLM invocations, there is embedding generation, there's a lot that's going on. And there is latency plus cost. With semantic caching, what happens is you define the similarity threshold, and beyond that threshold, anytime you have reached that threshold, all of the questions which are similar get clubbed into sort of a group, and then the responses get returned from the cache. So you're caching both the similarity plus the LLM responses in your Valkey layer. And what happens is, by doing so, you skip the entire pipeline generation process. And you're just going to the cache and retrieving results. Zero LLM cost, no latency, and sub-millisecond performance. All right. So there was actually a deep dive session on semantic caching. It was on Monday, so I highly recommend watching the recording on YouTube, DAT314. This goes much deeper into semantic caching. All right. This is how it looks like in action. Green is good, red is bad. With semantic caching on the left, questions 1 through 4, we get instant responses from Valkey. This is what we want. Smooth, great performance, keeps users engaged. More importantly, bookings complete on time. Without, same question triggers the full LLM inference every single time. What's worse is your users notice these delays, and then they start abandoning conversations mid-booking. Pattern 4 is interesting. This is where we get into a little bit of production architectures, tiered memory management. User says, book family flights there, avoid that airline. Referencing maybe context from earlier, maybe previous sessions, etc. The agent passes messages to Valkey for short-term memory in this case. We'll see it go through. And then Valkey, in this case, you'll notice it stores things like chat messages, which is your conversation history, session state, checkpoint. These are typically workflow checkpoints if your agent is going through certain ETL pipelines, jobs, or just a basic conversation. You can define checkpoints so it can pick up where it left off, similar to database checkpoints. All of that can be cached and stored in Valkey. Now, the beauty is you can actually have this intelligence behind the scenes. Your Lambda asynchronously extracts the short-term nuggets of memory, so all your conversation history, session state, checkpoints, etc., and push it out to Aurora as your long-term storage. Within Aurora, with PG Vector, the benefit that you get is you can do things like episodic recall. pgvector has relatively every past history stored as a long-term, with a session ID, memory ID, the whole interaction. And what you can do is rebuild that entire conversation looking at that long-term tiered storage. This will be, for this use case, things like this user prefers aisle seats or window seats. They have a budget, strong budget of maybe $300 and less. These are the things which will be persisted in the long-term storage, which can be looked upon across devices, across channels, every single time. And of course, you also have the MCPs thrown in. And within the MCPs, you can do things like you can extract these memory modules. You can list these memory events sequentially, serially. You can retrieve these memory records, rebuild it, etc. A lot of things that you can do with the agent. So this is sort of a hot or short-term and long-term memory separation. Where it gets really interesting is this sort of a tiered shared memory architecture with multi-agent workflows, which is what we are building for Flightly. So add travel insurance before you book my flight. Use the email from our support conversation. This is sort of a stateful multi-agent workflow where your shared memory state is stored in between ElastiCache and Aurora Postgres for the agent to do sort of seamless handoff. So you'll notice you have our orchestrator, in this case, Flightly's orchestrator. It has 3 specialized agents. You have your support agent, you have your booking agent, you have your payment agent. All of these share memory in both of these layers, your long-term storage as well as your short-term memory. Behind the scenes, we are still doing the same thing. We are extracting the short-term memory from ElastiCache, persisting it to Aurora. And in this way, you're basically sharing the state. And the workflow will be, your support agent queries Aurora semantically. It'll find last week's support conversation, extract the email. Booking agent will go and search flights, reserve them, and writes this confirmed booking state to Valky. That's your checkpoint. Payment agent will go and read this confirmed booking state and add the insurance and then process the payment. So all of this is orchestrated through a common memory layer. There is no context drop-off. There is no sort of continuity lost between agent handoffs. And states are synchronized in real time between the two of them. All right. We've looked at 5 different patterns. We've looked at different steps in building this conversational AI system. Now the critical question. How do we scale this to production? 1 million daily queries, high availability, cost optimization, security. So far, our agents are running locally on our laptops. Your MCP server, Aurora Postgres MCP server, is running as an stdio local Python subprocess on your laptop. What if your laptop crashes? What happens mid-transaction? You lose the transaction. Obviously, that's a no-go. How do we scale this? So this is where Bedrock Agent Core comes in. Just a show of hands, who's not heard of Agent Core? Anyone? Everyone's heard. One person hasn't heard of Agent Core. Yes. So Agent Core is an agentic platform to build, run, and deploy agents securely at scale. Think about how we run Postgres on self-managed servers versus Aurora Postgres as a fully managed server. Agent Core is your fully managed capability to run agents. It has a lot of components to it. We won't go too deep into it. There's a lot of sessions around for Agent Core. But at a very high level, runtime provides your local agents an environment to run at scale on the cloud. You are not running agents locally anymore. The beauty about this framework is you're not restricted to just Bedrock models. You can use OpenAI, you can use Anthropic, you can use Gemini, it doesn't matter. Plus, you can bring your own agentic frameworks, such as Crew AI, AutoGen, LangChain, LangGraph, what have you. Agent Core Identity gives you that secure sort of identity and access management for your agents, which is super critical in production. Agent Core Gateway gives your sort of a gateway to your MCP servers, your custom tools, your Lambda functions, your OpenAPI schemas. Your existing tooling or business logic gets fronted by Agent Core Gateway, and it gives you that routing layer to sort of make it more seamless for your existing application. There are a couple of other tools like Browser and Code Interpreter. Browser is, if you're familiar with computer use for Claude, you give your agent access to your computer, which you should not, to do things. Browser is used for that. Code Interpreter is more of a sandboxed code execution environment. But then you also have some other nicer features like Agent Core Memory, which also offers out-of-the-box short-term and long-term memory modules. And to wrap all this around sort of good guardrails and tracing of the agent actions, you have the Agent Core observability layer as well. So remember my Friday frustration? Same journey, completely rebuilt. In this case, Valkey caches the frequently asked questions, baggage policies, booking templates, email templates, and it returns these results in microseconds. Aurora with PG Vector handles the route information, looking up seat preferences, long-term memory, semantic search, all in 2-digit milliseconds. 9 out of 10 customers stay, 60% cost savings, performance that truly scales. And with that, Flightly is ready for Hawaii, and so are you. With that, thank you for your time. Mahalo. I do have a couple of resources to share. And if you do have questions, let's take them outside. But please do remember to complete the session survey. And yes, thank you for attending. Enjoy the rest of re:Invent.